Not on, right? I'm on. Okay, very good. Okay, it's my great pleasure to introduce Swati Sircar from AzimPremji University, and she'll talk about Platonic and Archimedean solids.
Thank you. So, we'll show you some stuff with this, and we'll share a journey that we had for over a few years now. And it has been a pretty colorful and adventurous journey, which started in a very interesting way. Okay. So we saw a craft project in some alternative school. These were circles with triangles, squares, etc. Inscribed in them. And then the polygons were joined along their edges, forming various solids. Okay, okay, cool idea. So we explored a bit and wrote up an article which is about the Platonic solids. So here are some of the pictures from that first round of exploration. Okay. Now one of these is here, and that's the first one, the tetrahedron, regular tetrahedron. Okay. So, okay, fun. Can you guess what we observed? All the circles are of the same size. What did we observe when we did this? It's a small thing. Of course, regular, that we knew. But if all the circles are of the same size, what happens to the sides of the polyhedras? What are you putting inside the circle? But not all have triangles, okay? We do have a cube. The second one, this one is actually a cube, okay? And this one, you can see it's a pentagon, right? So it's a dodecahedron. So there are at least 3 different regular polygons inscribed in circles. If the radius of the circles is same, then what happens to the side of the polygons? They will decrease, okay? Now, pragmatically speaking, what happened along with that is that sector, which is outside, not sector, segment, which is the flap that, that's the one we are stapling, that flap changed, okay? So for triangle, we get a pretty large flap, easy to hold, and so on. But as we progressed, the flaps became much, much smaller, okay? But we'll come to that later. But while doing it, it also generated a dream, which you guys can guess what it was. Any idea? Any clue? So we made these 5 solids, okay? And like, mode of what? Polygons. Which ones? Yeah, more regular polygons to make what? Yes, we will inscribe more polygons inside. Okay. So, well, technically all of them fit inside spheres. We'll come to that later. That was also there, but more importantly, I will come to the dream, okay? But what we did is, see, when we made this, we realized all 4 faces have to be different colors. There is no way to, otherwise have a symmetric distribution of colors, okay? Then this is the layout for the cube, okay? You can recognize the net of a cube. And this is octahedron. This is not really laid out as the net, but these are the pieces that went into making the octahedron. Okay, now notice we have 4, 6, and 8 faces, right? And number of colors are 4, 3, and 2. Do you see any pattern?
As the number of faces are increasing, the number of.
Yes, but this is the thing. In math, you shouldn't jump to conclusion too soon. Okay, I mean, see if the pattern persists. So the next two, so this is the dodecahedron, and this is the icosahedron. Now these have 12 and 20 faces respectively. Okay. Yeah, how many colors? Yes. I mean, this was a bit surprising. 12, right? So many multiples. And it settled with the highest non-trivial one. Okay. And this one was rather straightforward. There are 4 layers of triangles, 5 in each layer, and 5 triangles coming to 1 point, each vertex. So obviously you need minimum 5 colors. And 5 did it. And if you notice, the pattern is the same. It is yellow, blue, orange, green, pink. So even if you look here, yellow, blue, orange, wrap around, green, pink. So you just do that and that kind of takes care of it. Okay. So far, so good. So this had 5 and this one had 6. So earlier theory shattered. Okay. And that happens. Okay. So now if you look at these two, there are certain things that are common to both. The cube and the dodecahedron. Among all the Platonic solids. Platonic solids are those solids whose faces are all same. Okay, all edges are same, therefore the faces have to be regular polygons. And also, okay, that's not maybe completely true, but all internal angles are same, and the same number of faces meet at each vertex. Okay, so it's like the perfect solids, so to speak. Okay, the regular ones in the land of polyhedras. Okay. So exactly, and can you guess why so? She said the number of colors is half the number of faces. So for a cube, you have 6 faces, we needed 3 colors. For the dodecahedron, 12 faces, we needed 6 colors. Okay, so half. Why that halving? Yeah. So one of the thing is these are the only 2 Platonics which are not made of triangles. The rest are all made of triangular faces, and the opposite faces have same color. That's the thing. Okay, that's why the halving. Okay. Now these 5 can actually be put in 3 groups. Are you familiar with duals? Okay, it's a kind of neat concept. So let's take a 2D example. Okay, so let's say we have a rectangle and we join the midpoints to form another quadrilateral. What will you get? It's a special kite A rhombus, correct. Now, instead, if we take a rhombus and do the same, right? So they are very jiggery those, okay, duals of each other. Okay. Now, same thing kind of happens in the land of polyhedras also. Okay. Imagine a cube. Okay. So all of you have seen dice and so on and so forth. So you can imagine a cube. Now think of the midpoint of each square face. Okay. And join them. Octahedron. Exactly. Okay. Now, if you try to do the same for an octahedron, then you end up getting a cube. Right? An octahedron will have 4 faces on top and 4 faces at the bottom. So if you join the midpoints of these 4 faces, you will get a square. Okay. Similarly, you'll get another square. And you know, it's a perfectly symmetric thing. So if you rotate, you will get squares all around. Right? Okay. So, any guess what will be the dual of this one? A regular tetrahedron? So 4 triangles put together, right? 4 equilateral triangles. Yeah. You get exactly, it's the same thing you will get. You'll get no different shape, right? So these kind of things are kind of boring and very, self-contained. Okay. So they are self-duals. Okay. So that's that one. And then we have a simpler pair, which I just described to you. And the other 2, they form a slightly more complicated pair, but they are also duals of each other. Okay. Now, at some point, I may make a model of this, the outer one with transparencies and the inside one, a colorful one sitting inside someday. Okay. So this is fine. Okay. So now the dream. Okay. So that was to make all the Archimedean solids. Now in Archimedean solids, you again have all the edges are same. All faces are regular polygons, but not necessarily the same regular polygon. Okay. And whatever happens in one vertex happens in all the vertices. So in one vertex, if it is 2 squares and 2 triangles coming together, then that's what is going to happen in all the vertices. Okay. Now there is one Archimedean solid that pretty much everybody knows. Okay. And it's popularly called a food ball. Okay. If you ever pay close attention, at every edge you will get 2 hexagons and 1 pentagon. Okay. Now this is where I'm going to say something which I tell all math audience. Do not believe a math person. You should always check for yourself. Okay, so again, don't believe me when I say it's 2 hexagons and 1 pentagon coming together to give you a football. You should actually check. Okay. By the way, football manufacturing also involves a lot of math, how to optimize the process and all of that. Okay. And if you do only math, how that fails. Okay. So anyway, that's a different story. So at that point, we knew some of the Archimedeans were truncated Platonics. Okay. So what that means is, suppose you chop this corner. Okay, all the corner. So you'll get a triangle here, and all this with its corners cut, it will become a hexagon, because you are not chopping all the way to the midpoint, but a little bit. Okay. So So we knew if you do the truncation, then you will get 5 Archimedeans. So those, have to be color coordinated. Okay. So same color combination in the same order. But there are 13 Archimedean solids. What about the rest? So this is the picture of these two. Okay. So I don't know, can the camera zoom in? So, pink and green. Then I'll turn over to blue. Oh, okay, that's fine. But you guys got the sense, right? Okay. Yeah. Okay. And this is the rest of the pair. Okay. There's no way I could carry all of them. Okay. Then I will need a big box. So if you look here, you can see a little cut. We will come to that later. Okay. And as you may have guessed, these are all just stapled. No glue or anything. Yeah. So this was the next question. And so we did have a big aha moment. Okay. Before that, I'll show two. You see, they are not looking that exciting. Okay. Even if this was a pink and blue combination, still, what's the big deal? Okay. But then we did have it. By the way, these are also made with no glue, no tape, but the way they are staying put, and you can see all the flaps are actually inside, will reveal their secret a little later. Okay. So same color combination. Okay. Now take a look at this one. This is called a cube octahedron. Okay. So what are the faces? Which polygons are used as faces? Okay. And what colors are you seeing? So the squares are pretty much the same colors, right? Yellow, pink, green, and on this side also yellow, pink, green. Okay. Now, if we look at it this way, red and then 3 blue. And if you look at it this way, then blue and 3 red. So 4 blue, 4 red. So that's 8 triangles and 6 squares, right? Now for those who are joining online, okay, so this is the net. Okay. And if you basically unpack these two nets, if you unpack these two and combine them to make one solid, that's what you will get. I mean, physically, actually, you can do it with these. They can be taken apart and, put together again. So this was like, huh? So then what happened is, okay, so that's if you truncate this one, then you get that. Yeah. Yes, cutting the corner so that the resulting, so that cut will generate a regular polygon and the resulting faces will also be regular polygon. Yeah. So this would be roughly this size. Okay, if this is what is the base, then okay. And if you make the cuts deeper, so you are cutting so that from midpoint to midpoint. Okay, if you make that kind of cut, then you won't end up getting an octahedron here, but a smaller square. So that's what happens. Okay. And then snub cube. How do you get the snub cube? So imagine, this line, and suppose, you replace these two right isosceles triangles by equilateral ones, then you will get that. Okay. And you see the top one, or rather the top right one is with the pink, and the bottom left one is with the yellow. And the same pattern continues. Okay. However, this is not the only way to get a snub cube. You can get it the other way also, depending upon how you are splitting those squares. Okay. So far, so good. These were pretty easy, relatively speaking. By the way, let me show you the net of a snub cube. So in snub cube, what happens in each vertex? There is one square and 4 triangles, right? If you look at it, any standard picture in the internet uses one color for all the squares. And since there are 4 triangles, they use 2 colors. Okay. We'll show you that picture later. This is how the net looks. Okay. The other one is mirror reflection. Okay. And it kind of helped keep track of how many triangles and how they're grouped and all of that. Okay. But still, so far the journey was pretty smooth. Also, these were made on Mathegon polypad. Okay, it's a great website for virtual manipulatives. And the best part is you make that net and then you can ask it to fold. It will actually fold to give you the solid, which you can then rotate. So you have seen pictures of both, right? So that's how you got pictures of both. Okay. So, yeah. Now, this is from the internet. This is how cube, octahedron, and you can count how many Archimedean solids are here. They are all linked up. Okay. If you go to Wikipedia, Archimedean solids, this picture is from there. Okay. It has a lot of information and, you can look. I'm not 100% sure, but it's like you kind of shrink the faces and make the edges widen to become rectangles and then square, something like that. Okay.
Why snub is not connected?
Come again?
Snub is, why is it like not connected?
I don't know. Okay. So as I told you, see, in case of snub cube, all the squares are red. Most of the triangles are blue except for some which are yellow. Okay. Here's a more colorful version of the same thing. So this is where it is a truncation. Okay. This is where the cut deepens all the way to midpoints. Okay. And these two are kind of linked. And yeah, you get 2 versions of snub cubes. Okay. So this is a more colorful version of the same thing. Okay. So far it was easy, Now these two should also give a similar situation. I mean, that should be a natural hypothesis, right? Okay. Dodecahedron is the one with pentagons, regular pentagons. So one pentagon and then 5 more. So that's 6, 6 more, so 12. Icosahedron, that's the one with triangles. Okay, you truncate that, you get a football. Okay. So this is the situation. Again, so truncation, making the cuts deeper, more connection, and then the snub one. Now you may wonder why here there is only one snub dodecahedron. Why not 2? Technically, there should be 2. However, I couldn't manage to get the other one. I have no idea why. So I'll tell you what happened. So one big difference was colors, number of colors. Coming up with a color scheme that is, symmetric and all. Okay, it became way more complicated. Second, if you are thinking of the cube and the octahedron coming together, it's easier to visualize a cube, right? Because you have one pair of faces for each dimension, right? But the moment you are in dodecahedron, it gets more complicated. And so here is one thing. People say this a lot, that math is abstract, etc. And it is. The thing is, probably they don't get it, what it really means. So if you are trying to create something very concrete, okay, one option is to go for a lot of trial and error. The other option is you plan it out so that when you finally make it, it's what you want. That demands a very high order of abstract thinking, and in this case, spatial understanding. So it's easy to scribble out a net, okay, and just label the colors. But then trying to visualize which edge will fall to match which one, how they will come together, is not easy, okay? So getting this guy, okay, was tough. And not only this, there are 2 more that come after this, okay? Okay. This one is the largest. So all of these, this is 4 centimeters, okay, because 3 centimeter was too less. So these are 3 centimeters. It was, is it 3? Yeah. So that became too small. And the flaps also was not big enough. So we've switched to 4, 4 worked perfectly. This one is this big. Okay. So, imagining like that this one is polar opposite to that one is fine, but ensuring that this is polar opposite to that, and etc. And then placing the, sorry, oops. Wait. Placing the triangles around was pretty difficult, okay? Maintaining that same thing. So now this is where there was a roadblock. So for snub cube, You just make a mirror reflection of the whole thing, and that folds to give you another snap cube. Somehow with this, that didn't work. Okay, so this one folded, this one or its mirror, one of them folded to give you a snap dodecahedron. The other one, no matter how many times I tried, it won't fold perfectly, like, something went wrong somewhere. So I don't know whether it is imprecision in drawing which is not showing up, okay, or it is something else. Now, this is the only model we are yet to make. We ran out of triangles, basically. When initially we thought we will make only one snap cube, but then we did two. So this is the one we are yet to make, okay? So then we will know for sure if both are mirrors or if there is something more going on or whatever, okay? So the icosahedron, which is this one, this is roughly this size. The dodecahedron will be this big, okay, and as I said, ginormous. Okay. Again, no glue, no tape, nothing. And this is the whole family except the snub dodecahedron. Okay. So if you come to our lab anytime, then you'll get to see them. Okay. The interesting thing is, this is how the journey started, and this was a very ambitious project. But by the way, these are all hand drawn by some of our students, like you, first year students, who were, I would say, royally tortured, in the sense, if a polygon is not regular enough, then they were rejected. Okay, so it took a lot of time, but then now they can bask in the glory. Okay, so around, I think, 5, 6 people helped in making these. Given that students were doing this outside class and other work, etc., took few months, slow and steady. We didn't put a deadline to it. Not the nets, they made the individual pieces, like so many octahedrons, so many decagons, or not octahedrons, octagons, decagons, and things like that. Okay. Then coloring them, cutting, and then, I put them together. Okay. Let me pause here. Any question? Yeah.
Can you just keep snubbing it?
Well, you can try and see what happens. Maybe plasticine will be a good idea to do that. Okay, so I'm guessing what might happen is you may get nice polyhedras. They may not be Archimedean, in the sense all the vertices have the same combination of faces. That may not be there, but right now I'm just guessing. It's best to, try and see what happens. Okay. And usually people start with simpler and then go to complex. You may want to start with just this one and see what happens. Okay. Let's see whether it will remain self-dual or whether it can generate anything else. Yeah. Any other question? Okay, so when some of the faculty who teach UG level courses, they saw it, they were like, we can use this to discuss symmetry groups. Okay, how they're going to do it, I don't know, but yes, that can be done. So whenever you think of any rotation, right, you can represent it as a matrix, right? And today you are learning about those. And there is a lot of symmetry in there. So maybe you can figure out what kind of rotation keeps it invariant or maps one thing to the other, etc. Okay. So for me, the main thing was, once I realized that these can be combined to make this face-wise, this is not highlighted anywhere on the internet. They show how if you cut this, okay? So if you go from midpoint wise, etc., you deepen the cuts, etc., or you cut this one, how this converts to that and how this converts to that. That's what they say. But this kind of combining faces to get this, that aspect was never there. I mean, you can imagine that, lot of surfing, net surfing went on alongside. So that I found to be something quite interesting. Okay. So these are rejected squares, okay, from that project, because they're not all perfectly right angle or not all sides are equal, something like that. But then one of our BSc B.Ed students, she wanted to make all possible nets of cubes, and then these came in quite handy, because you can join these any way you want very fast. Okay. And you can actually check whether it will become a cube or not. In this case, you can see that it will not become a cube. There is an overlap here and this one is empty. Okay. And so instead, if you do something like this, that works out. Okay. So these rejected pieces have become very important now. Okay. And this is exactly how each of the modules that make these, all of these. So there is a circle with the regular polygon inside, and all the flaps are cut up to the midpoint. Okay, so the inspiration is from some childhood mechano type toy. Okay, and they interlock nicely, conveniently, and you can, explore and come up with various shapes. Okay, so here are the pictures. Okay, back and forth. So all of these are made from old posters. Okay. And then another dream. Okay, a shape kit. So what is a shape kit? Now, before going into that, how many of you have watched Shakuntala Devi? Shakuntala Devi, that movie. Did you notice that she was doing cube root? Now, how much of cube root have you learned? I mean, cube root of 125, yes. But the way we find root 2 and root 3, and we can actually figure out how far it goes by hand. Similarly, cube root should be possible, right? But it's not taught at all. But it must have been there at some point, because in certain places, that movie also says cube root was something quite popular, right? I mean, unless people knew about it, how would she impress them? Okay. So one thing that happened, and this is a story I will tell in a very, very short time. Worldwide, and this is where politics influences education. There was a big shift in the school mathematics education after USS successfully sent something into the outer space. Okay. Now that was a big blow to the US ego. Okay. They did it before us. Okay. So then, like, how did they manage? And it turned out they were, USSR, were teaching calculus at school level. At least they were starting that at school level. And therefore, the number of engineers and technical people they need with the knowledge of calculus was ready by the time they finished college. Because in such large projects, you need a lot of people. In US and probably the rest of the world, calculus was not there in school and began only at the college level. Okay, so if they're successful, and this is one of the reasons why they're successful, then obviously that has to be replicated. Now, you have a child is in school for, let's say, maximum, I don't know, 10, 15 years, right? Finite number. Each year has a finite number of days, and each day has a finite number of hours, and none of that is empty, right? There is an existing syllabus, etc., and probably still then they have the difficult job of covering the syllabus, completing it, and all those things, right? So if you want to now bring in calculus, then something has to go. So what went was three-dimensional geometry. That was just out. Think about it. You have all studied conics, and you know why they are called conics, right? Now, how is the center of the parabola linked to that cone? Not center, focus of the parabola. How are the foci of an ellipse connected to the cone that generated it? Most likely the only treatment you have seen of conics is numbers and algebra and symbol manipulation to a large extent, right? That will probably not, and it's all on 2D, Cartesian plane. That may not suffice in figuring out, I mean, we are talking 3D here. Here is a cone, and you are slicing it with a plane which may be parallel to one of the slant sides, then you get a parabola. If it is not, and it cuts both, then you get an ellipse, right? So how are these 2 points inside the ellipse linked to that cone? Human civilization knows the answer. Okay, look it up. Okay. So overall, few generations probably missed out on spatial understanding, especially when it comes to three-dimensional things. Okay. So there are many people who will see a floor plan or a building plan and all to be able to make sense of it. And if these people have to, make house or build house or something, I'm not saying they are going to build, but if they have to supervise or give feedback, etc., if they don't have that sense, then it's difficult. Okay. We know architecture students who don't have that strong 3D imagination. Even surgeons need to understand things in 3D. It's a three-dimensional thing, not 2D, right? So one of the things that has happened in our country, since 2005 is there has been major shifts in school education for the better. And one of those shifts is to bring back this intuitive sense about 3D, etc., back into school, back into classroom. So, and teachers do struggle with it much more than the children do. So this is an attempt towards that. So the kit will have a collection of polygons, not necessarily regular polygons, but polygons with rounded flaps on each side. Okay, and those flaps will be cut halfway. Okay, what do you do with them? You join them together to form different solids, pull it apart gently so that you can make other new ones also. It's kind of a Lego version for geometry. Okay, that's the whole idea. Now, whatever you see here are all made that way. However, these are too small, again 3 centimeters, these are 3 centimeters, okay, and that's too small. So these are the all possible cuboids. Okay, the picture there, it may not show nicely, I'll show you here. To start with, a cube, all dimensions are equal. Now, if you elongate that cube, you have this 2 square faces, and the third dimension is longer. This is what you can call a flattened cube. Okay, so 2 square faces and the third one is shorter. And then the fourth one, where all 3 dimensions are different. Okay, so that's the all possible combination. And then, now this we know. Can we join rhombus? Okay, identical rhombuses, rhombi, to form a similar thing like cube? Now you can explore that, and yes, it can be formed. Okay. Similarly, this is the slant version of that elongated one, and slant version of that one, and of the cuboid with 3 dimensions. Now, while doing it, there was again some interesting observations, like where the 2 faces need to be mirror images of each other in terms of the cuts and so on and so forth. Okay, but okay, so that was there. So here are the remaining pictures. Okay. Now another thing that came. Okay, so here you can see a collection of pyramids. Okay, same thing. Okay, can you describe them? Yes, so there is triangle, square, then hexagon, octagon, and decagon most likely. Yeah, what else? Yes, however, one important thing is all these slant faces are actually identical. All slant faces are identical. Okay, so that is important. Now, this is actually a quite easy question.
Decreases with the increase.
Does it decrease? Okay, can somebody give a very commonsensical argument? Yeah, so as the number of sides of the base increases, the number of triangles increase. So that's a very clear increase. The other thing is, as the number of sides increase, the base area increases. So it's very, very clear, right? And you don't have to do a lot of calculation to figure this out. Okay, see, there are mathematical proofs which are brute force, lot of calculation, and then there are those which are elegant and you get the idea. Okay, so this is one where you can get that idea and yeah, makes sense. However, if we are talking about surface area, then next comes volume. I don't know, I haven't solved it. Surface area does increase, but height is decreasing, right? So it is definitely 1/3 base area times height. Base area is increasing, height is decreasing. Now we have to look at the rate and figure that out. Okay, I haven't worked it out, so feel free to do it and let me know. Okay. So the university, AzimPremji University, is part of a foundation which runs several schools. The physics teacher from one school was here earlier this month, and he walked in, and then these are questions that he raised. Okay. Now I have another important question. See, one thing about school mathematics is, as a mathematician, when you tackle a mathematical problem, you can use whatever tool you have. But the moment you are thinking in terms of school mathematics, you have to keep in mind, okay, at which class is the child facing this? Does the child know trigonometry? Does the child know rational numbers, or is it only up to integers now? Okay, so those are constraints, and you have to see, is the problem solvable within those constraints? Can you solve it with minimum resources? Okay. Now, again, I don't know. So you have the fixed side of the base, and you can take it to be 1 if you want, or S. Okay, and as number of sides n varies, you somewhere need the radius, probably. Okay, or even not the radius, you need some way to get to the height and stuff. So I don't know. Yes, that will give you a hypothesis, definitely step 1, but we mathematicians are very picky people. We are never satisfied till we cross our T's and dot our I's. Okay, so yes, absolutely you can do that. Okay, then what? Okay, so I would like to leave you with these questions, and that's it.
So the last talk for today, Professor Susy Varughese will give the talk from IIT Madras. She'll speak on plastic bags to brains.
Okay. Yeah, so you must have been listening to math all the time. Now I'm going to talk to you something slightly different. Okay, this is a popular talk to give you, but there's a lot of math also embedded in understanding these materials. I'm not going into it because maybe some of you may get into applied math, or try to understand some of the fundamentals of these materials. It may be very intriguing. I don't know how much of you are exposed to in your usual school curriculum or so far, you have learned anything about polymers. Have you heard the term polymer? What comes to your mind when you hear it? That's a little more scientific. Any applications, anything that you see around? Polythenes, yes, that's what. PVCs. What else? Huh? DNA is also a polymer because I put something there. Yeah, so what else is a polymer? Anything else? I'm just asking the term polymer, what brings to your mind? Huh?
Multiple carbons.
I'm not asking about the scientific aspect of it to define what is a polymer. I'm asking a question when you hear polymer, does anything ring in your mind? Like, what comes to your mind? No, that's again a scientific definition. Okay, all of you are giving more scientific, definitions to it. So basically, if you look around you, do you see polymers? That's my question. So tell me some examples. Rubber, plastics, those are common names. Huh?
You can say almost everything is polymer.
Everything is polymer. What do you mean by that? There are metals also around here. Are they polymer? Okay, this surface, is it polymer? Why? What? Which polymer? Wood is a polymer? Huh? Pardon? Fabrics are polymers. Okay, fabrics means that's a very generic term. You may be wearing some different types of fabrics, right?
More synthetic fabrics are polymer.
Only synthetic fabric. Only synthetic ones. Only synthetic. Only synthetic or others?
Not sure about that.
Okay, what are the other fabrics you use other than synthetic? Cotton, wool, nylon is synthetic. Silk, you have heard of silk? Yeah. Jute, okay. So there are a lot of fibers also coming in from your. So we will come to that. So all these materials that you have with you around, they are all polymers. It doesn't ring when we say polymer. Mostly we think about some plastic bucket or that carry bag. These are the thoughts that come to our mind. So one thing I said, like this wood is also polymer, but it's a composite. There's a term difference there, but fundamentally there is a polymer involved, cellulose. Now, forget about that alone. So look outside, you have plants. Now, what are they made up of? Carbohydrates. Are they made up of carbohydrates? Okay, so you get the wood from the plants, right? Okay, so there may be something that is associated with it, also polymer. Cellulose is one part. Then you must have also heard about hemicellulose, lignin, all these things also as part of plant cell wall. Okay, that's what plants are made up of. What about us, human body? What is that made up of? Any polymer involved? Lots of polymer. Tell me one part. Let's say skin. Is it polymer? No, I'm coming to some, something that makes it. No? What is skin made up of? What makes, so now when we talk about all these things, what makes you feel that this may be a polymer, something may not be a polymer? Is there any generic feeling that you get? You think this is metal? No, that's sure about it. Is it leather? No. Is it rubber? More rubber-like, right? Don't you think it's more rubber-like? Your muscles, it's more rubber-like, right? I can pull and relax, right? Or no?
Yeah.
No, yes or no? Yes. So is it rubber? So there is some things which are coming to our mind when we see these materials. Okay, so one is that there is a clear distinction that you're trying to say between metal and non-metal. You are able to distinguish. And now, if I show bricks, for example, these are also materials. So we have these different classes of materials which engineers and others work with. So we classify them based on certain aspects of them, certain properties and things like that. So, but these properties are also involved in nature, also in various aspects of biological materials. Like our body, which is made up of muscle. Muscle is again, I'll come to that. I mean, they are all biological polymers. Okay, whether it is muscle, whether you're taking skin, whether you're taking blood vessel, whether you're taking blood. So, okay, blood cells, for example, they are also, containing polymers. So basically, what is polymer? So you would have all studied in school that that polymers are made up of this, what are known as very, very long chains of molecules. So what is meant by these very long chain molecules? And these are the common constituents of polymers, like, carbon, hydrogen, and all that stuff. But if you look, close by, they look like long garlands of things, or like take a cup of noodles. These chains are lying around there. So now if I take this material and look closely inside, I don't have any tool to actually see those molecules. I don't have any tool to even see the DNA inside my cell. Okay, so but at the same time, it's a very, very long molecule sitting inside this material as well as in my cells, and both are performing different functions. What I mean by function is, it can be some mechanical property, maybe my frame of this specs. It's also a plastic, which is also a polymer. And if I just open and if I am able to see it, it's this kind of noodle-like structure which is sitting inside there. And but it has this molecule, atoms and things like that, which constitutes them. So I have written that there are natural and synthetic polymers around us. So that's what we classify them as. Synthetic means we make them from some petroleum resources and things like that. So most of the synthetic polymers that we see around are carry bags, and our life today is almost unimaginable without polymers. Even this wearing this mask, this is also some form of polymer. So I'll come to some of these applications when you will know what are all the different kinds of polymers that you come across. So they are classified based on where they are originating from. They could be natural, there could be synthetic. Then you have, those are little more chemistry oriented, molecular architecture and all that. And similarly, you may be knowing, response to heat also. There are thermoplastics and thermosets and all those terminologies you'd have heard. And then you also would have heard terms like rubber. Then you would have heard paint, varnish, leather, adhesives, fibers, name it. These are all polymers. But normally, we also associate polymers as insulating materials. That is also one reason why we are able to get power to all kinds of devices, all our switches and other things. Though the current is, the electricity is carried through a metal, when it reaches us, it is through a non-conductive medium that you have to use for switching and things like that, because you need an insulator. But today, from 1970s onwards, there have been discoveries to show that polymers also can be made into conducting materials. So there are semiconducting polymers today in the world, which is making life very, very different. You have what is known as flexible electronics coming in. So you would have all heard about electronics. There is a, what do you call, the printed circuit board, which is actually driving all our devices inside, which is made based on what is known as silicon technology. You heard of silicon, right? So silicon is the atom, Si. So the silicon is a semiconducting material, and that is the reason why you're doing that. And the problem with that is it is a rigid system that you develop. But today you have devices which are foldable, flexible. Tomorrow you may have already it is in work coming in, that things which can be folded and put in your pocket. How are these things made possible? Okay, so there has to be material science developing hand in hand to make these devices flexible, foldable. For example, this touch screen here, all these are possible because of this material, polymer. So in that, this conducting polymers is also becoming a big class of material, which will be much cheaper and much easier to fabricate in comparison to silicon-based technology. Only thing is that when it comes to life, etc., polymers have less life in comparison to silicon-based technology, which is more hardy, where you can store information, etc. I also mentioned in my abstract that there is something called DNA computing. That is, have you heard of it? DNA computing, a term. Some talk by somebody? Yes, yeah, okay, yeah. So what is DNA computing? Okay, So not just that, these molecules, when it comes, I'll show you what the DNA structure is. So you can use it for information storage. So how do we store information currently? Using metallic or inorganic materials like the silicon and or other devices which are made from such materials. But it is possible to store, for example, information in DNA. So the advantage is that for the same volume of information that you store using a metallic or inorganic device, you may require 1 kilogram of material or 1,000 kilograms of material. You can store that in 1 molecule of DNA. Okay, so I'll come to that, why this becomes important. So it is also, so why this is important is that we also have to see that these polymers are not dead substances. Why? Yes, the information transfer, okay, for all living systems is through a polymer. Which polymer? We are all what we are. You and me are whoever you are, is because of the genetic information. Where is it in genetic information transferred? DNA, everybody knows that. How is it done? When it comes to that, it is just a material science. Yeah? The amino acid sequence and things like that, But it is a live information transfer. So if we want to transfer an information through a material device, it is so complicated. And here is nature transferring information, whether it is plants, animals, or virus, or anything that you look around. One molecule is responsible for the whole of information storage and transfer. You know that your DNA, if it is when it is replicating, if it is just tailed off a little bit, what can happen? Yeah, you would have heard of, right? You can have genetic disorders. You can have some limbs or something maybe formed, may not be formed. And you also have a process where two parents, the genetic information from two parents come together and combine together, and you get the new information, right? So there are again two molecules are involved. So now let's go there. So before that, I'm just showing simplest of the polymers, that is polythene. Okay, in comparison to all this natural polymers are very, very complex. But if you take the simplest of the polymer in terms of structure is polythene, it has only carbon and hydrogen. And what is known as the repeating unit is this CH2. It will go on repeating. You have any idea how much it should repeat to get that polymer? A million. CH2, double bond CH2 is a gas, ethylene. Okay. So when we engineers, we polymerize it to get what we call as the, that carry bag material. So it started as a gas from what is known as petroleum industry. And when you apply a lot of pressure and temperature in the presence of what is known as catalyst, your little bit of chemistry, this whole molecules will come closer and closer and start combining. So this double bond will start opening up and it starts forming like a garland. Okay, it's not, this is an addition polymerization, what we call. So like if you take each of them as a bead, they're combining and forming a very long chain. So so I said it starts as a gas. So now when you start applying pressure, what will happen? It may become, gas will become liquid. So what is polyethylene? Liquid or solid or gas? Solid. So you may have to apply a lot of pressure, right? And also many of those atoms or molecules have to combine together to get that solid. And now the next question is, how do I know that it is polythene that is formed that I can use for a particular purpose? So as my job, for example, is in designing such things. I mean, using such materials to design various things. So we need to know, for example, whether it is actually formed into that polythene. I am not synthesizing, but somebody will synthesize it and give it to me. I need to know whether I can use it for carry bag or whether I can use it for something else, right? I need certain properties. So people who synthesize it, they'll stop the synthesis at certain point to know that this many atoms have combined together and formed into that required solid. So when I'm saying solid, I'll tell you some more secrets are coming, okay? It's not actually a solid. Is it a solid as a question? So we'll come to that. So this is the polymerization process. Don't worry about the chemistry. So this polymer, when it is forming, As I said, they can go on. As I said, you said, millions may be forming. So the minimum molecular weight people, try to say that it's a polymer is formed is when the molecular weight, there's something called molecular weight you all could have learned, right? So when the molecular weight is reaching 10 to the power of 5 and above, okay, is what we start calling it as polymer. So before that also, some of them may be, so we call it oligomer and all. Poly means many, mer means unit. So normally this many units have to combine to get that what we call as polymer. So then an interesting thing is, as I showed you, this way if I take and look, most of the physicists may want to just look at it like this. Okay, it's a very, very long chain. So when I have a chain like this, okay, and I want to understand what it is, especially in the case of DNA and all, it is not like this plastic. That plastic bag if I take, or this bottle if I take, this is made of another polymer called polyethylene terephthalate. So if I take and look at it, there are so many of these chains packed and sitting inside this. Okay, so for me, it's important to know how these chains are sitting inside this. Are they sitting, like straight like this? Or are they sitting like this? I have no idea. What about our DNA? How does it sit? Huh? That as a helix. But helix is, a double helix is the structure. But inside the cell, do you know what is the size of DNA? Very long, very long. So when you're talking about this, we are talking about molecules now. When we talk molecules, water if you take, what is the molecular weight? It's 18, right? Yeah, we are talking about 10 to the power of 5 and all. So you can think it is really humongous. And we are saying that it is sitting inside the cell. What could be the dimension? What should be the form? What is the size of the cell? Millimeter, micron, microns, right? So if you know virus and bacteria and all, they are all like single cell organisms and all. They also have this DNA and RNA sitting inside. Those DNAs, if you look at, you may look on the internet and then find out what is the length of a DNA chain. So what could be the form in which that's single cell sitting? And many physicists and mathematicians also are interested in finding out many properties related to this chain. So we consider them as, so this also is considered as a what is known as, so if you look at, they have two things. One is polymers as a single chain. If you take, there is something called a configuration, which is based on all the stereo regularity, where the head or tail, etc., coming, etc. That comes if you are taking polyethylene and all, it will be similar because CH2 is repeating. But you would have also heard of PVC, polyvinyl chloride, right? So if you change one H with a chlorine, it becomes PVC. You would have done this basic chemistry. So now when this repeats, it can have a head and a tail, let's say. So whether the head and tail will come or tail to tail will come, head and head will come, etc., will become a lot of statistical combinations are possible. A lot of statistics is involved in what is known as this polymer when it is formed. And also there is this is one kind of one monomer. I can also combine it with other monomers, okay, and get some other properties. For example, you would have also heard of styrene butadiene rubber, SBR. So it's an example of two monomers, styrene and butadiene taken and then combined. Styrene, when it forms on its own, it forms your polystyrene. All your, that cups and whatever things that you take, its structure is something like this. It has, this is the repeating unit. So we put it like this and form polystyrene. And polybutadiene is CH2, CH double bond CH2. Okay. So this is again, it can also repeat. This thing, when it polymerizes on its own, this forms a rubber. Okay, the feeling of rubber. This, when it polymerizes, it forms a plastic. Okay, very interesting. What am I talking as plastic? What am I talking as rubber? This water bottle is polystyrene, polyethylene terephthalate, PET. which is a different monomer. Okay, that you have to go and figure out. I also don't know all the formulas. I'm giving some easy ones for you to figure out. So I'm saying this, if it polymerizes on its own, this form that polystyrene. That's our styrofoam cups and packaging and all those things are styrofoam. Now this polymerizes, it forms a rubber. Rubber, you know, your tire, okay, or your eraser, rubber band. All these are soft and rubbery materials. Now there is a polymer which is combining these two monomers and synthesized, which is your SBR, for example, which is also rubber. Or you can also get, so these are known as copolymers. So people, so this is where a lot of statistics is also involved. In the sense, which way are they going to combine? People have all permutation combinations possible. Like I can take 2 of this and 2 of that, 3 of this and 2 of that. Random copolymerization is possible. So all kinds of possibilities are there for synthesizing people. And there are materials available in the market based on that. And their properties can be very, very different based on that. So materials people do a lot of synthesis. So these are all stereo regular and all these arrangements. Then there's another interesting property with the single molecular chain. That is, you know, as I said, it's a very long chain. Now, as I said, it is, let's say it's a DNA chain or whatever. This is one end of the chain. Are you able to see it? Okay. So this chain. Okay, so physicists are interested in this chain. Okay, they want to know, or others also may want to know. Like as I said, DNA. This is sitting inside, let's say, your cell. Okay, so now the question is, what is the size of this DNA inside? What geometry it is going to take? So one of the properties people are interested, that is known as conformation. Means how this molecule is arranging itself in space, orienting itself in space. To understand this, they use what is known as an ideal polymer chain. Or this ideal polymer chain is a mathematical concept, ideal chain, which is considered to be infinitely long. So it has some properties, and it's volumeless, and it is made up of not those monomers. I'm going to convert that into some, let's say, n segments of L length each. Okay. So if I give something like this, okay, so this is L1, L2, L3, etc. Okay, Ln. So what are the things that we can understand from this chain? So one of the things is, if I know there are n L length segments of n chains, I know that if I pull the chain fully out there, the total length will be n into L, right? So let's say this is called the end-to-end distance. Okay, I can consider this maybe as a vector or something. And so this distance is known as end-to-end distance. It will be n into L. Okay. So the other thing is, I do not know how it is actually lying. Okay. So as I will consider each of this segment having a vectorial length. Okay. So this is a vector. This is needed for me because, as I said, the last point here is this ideal chain is formed of freely jointed links. So if you have this n segments or n links here, I'm also saying freely jointed. That's an interesting thing to say, that each of this link is capable of rotating 360 degree. So what does this mean? So now if I want to calculate what is known as the end-to-end distance of this chain, So what property do I get? So this R I'm going to, that R is different. So this R, if I fully extend it, I get a length, and that I said is R is equal to NL, I can get. Now I have another vector which I'm going to define here called end-to-end distance. Okay, so it's a vector, and I want to find out what is that R. Can you? I have given some qualifications here. Volumeless implies that you don't have to worry now in this calculation at the moment. Is it important for you? If I want to calculate this distance, what do you do? Huh? Yes. So these are all vectors, okay? These segments have length L each, L1, L2, etc. And so you're trying to find out the distance between the ends. What is the complexity in this problem? Is there any complexity? Huh? Yeah, but you have to define something now. So because this is a freely orienting chain, what does that mean? At any given instant, it can take any random orientation because it's rotating. So there is a whole lot of R possibilities here. So statistically, how do you determine that? Then you have to do something like either at a given instant, you can take many average of many vectors and do that, or you can do many chains simultaneously and then average them. So it's a statistical property, and you can determine the mean square, what is known as mean square end-to-end distance. Because if you just sum it up, it will become 0 because all orientations are equally probable, and then you will end up with that. So we determine something called mean square end-to-end distance, which happens to be, maybe you should determine it. You can go and probably try it out. Okay, so anyway, I'll just show it. So this is what is known as a random coil structure for polymers. So this is one property which physicists are interested. Others are also interested. Next question is, now if I apply force and try to stretch this chain, what happens? Okay, this happens in physiological and biological conditions also. Many times polymers are under what are known as mechanical forces, and these chains can get elongated. So what happens is this. Now, so this ideal chain is a very ideal concept. In actuality, any molecule will have what is known as bond angle restriction. So if I take CH2, CH2 and all, there are bond angle restriction. So you'll have to sit and calculate actually what is the conformation of a polymer chain if you know the bond angle restriction. So we first calculate ideal polymer chain, then we go into this real chain where you give the actual constraints related to that. Okay, so in addition to that, as I said, the physical properties of this stretching, how much force is involved, and whether it will form a, the number of degrees of freedom for rotation will keep decreasing when you keep on pulling it. Okay, so it will go to 1 when it is in this fully stretched form, number of degrees of freedom of rotation, right? So one immediate corollary is that you would have all seen rubber band, right? You pull it, and when you release it, what happens? It goes back to that state. Any explanations why it should be happening from this much? Huh? So it is that rubber band also has all this coiled polymers sitting inside, and when you're stretching, it's going into this fully extended form. Okay, even if it is not fully extended, it may be attempting there when you're trying to pull. So because it is in that coil state, it is able to extend a lot. Now you can ask a question, if I stretch this also has coil polymers sitting inside. Why are they not stretching so much if I stretch? Right? And this cloth is also polymer, but it is also not stretching. So there are so many other things coming. I don't want to complicate it now. So they are not in the same physical state. That's one of the reasons. So plastic is not plastic, rubber is not rubber, etc. is coming. So because they have something called a physical state in which they are in. So rubber is actually existing in, I'll come to that little later. So basically, so as I said, so when it goes back means, this is the state in which the number of degrees of freedom is less, means the entropic state is, the entropy, have you heard of entropy? Entropy is related to what? Number of degrees of freedom, right? So, so the higher entropic state is the coil state. So it would like to go back to the higher entropic state. It is like pressure. Let's say you have a gas molecules, you apply pressure, so the number of degrees of freedom decreases, and when you release the pressure, molecules will go apart. The same story happens here. Here again, the chains will go back to their original uncoiled state. Pardon?
What are we trying to accomplish
by stretching? Yeah, by stretching you will do a lot of things, no? The rubber band you are able to put around something, or your balloon you are able to blow. So many applications where you require it. Okay, we control it and use it in various ways. Okay, for example, this mask when I'm wearing, I don't want it to become too much stretched or less stretched. I can control it and design and say that, this is the stretching. Or, when I'm wearing something, I know how to control where it will go. Okay, when we design with materials, we know what is behind, how much it can be stretched, when I apply certain force, how much it is deforming. So this single molecule is deforming inside, but there is a macro scale deformation also. That is what we see when you deform the rubber band or take this bottle and try to crush it. These are all examples of mechanical forces being applied on it. So the material is undergoing some kind of change or deformation, what we call it. In labs, yes, in labs we do it. You mean to say that how do we stretch it? Oh, we make standard samples, which means, we shape them and then we attach them to some machine which has this control load application capability. So for example, I know how much force I'm applying. So once I know the force I'm applying, force divided by the deformation will give you stiffness, or stress by strain, you all know, right? What is stress? Stress is force by unit area, and strain is how much it is deformed. That is to the original length, how much it is deformed. So if I know force by unit area, I know what is the modulus of the material. So when a material is soft like rubber, modulus is low, and when a material is like this stiff, its modulus is high. Means so this can be done in so we all have a lot of equipments which test these materials. So if you give me a material, I know how to test it and tell what will be its modulus, how much it can deform, things like that. So those are mechanical properties. So by the way, this is our DNA's complex chemical structure, and the typical DNA contains this much, 80 million base pairs. So you can imagine that polyethylene was so simple, only carbon and hydrogen there. This is like a very complex thing with base pair, right? That so I'll just probably go to the next slide. So this is your DNA, right? So it has all these complexities and with more number of atoms. And then this I'm using from Wikipedia here. So there are so many of these things that you can read it. DNA is a polymer composed of 2 polynucleotide chains that coil around each other. Now you understand a little bit of coiling also, right? So this coiling again has to do with the chemical structure. For example, if I take polyethylene, it because of its bond angle, it does what is known as a zigzag arrangement, like this. The molecule will look like this because of the bond angle. So these are all carbons, look like this. But now here only it's hydrogen. Now you would have also heard about another polymer called Teflon. Have you? Where is it used? Microwave. Tawa, dosha tawa, or your iron box, for example. Microwavable? No. No, Teflon, I don't think so. Teflon is mostly used in non-stick ware. Okay. So it's also a polymer. It's a plastic which is non-slippery. So a very interesting thing about that is this Polyethylene is looking like this. Okay, as I said, it has some bond angle and all. In this Teflon is, you replace all this H with fluorine, polytetrafluoroethylene. So what happens is that fluorine is a big atom compared to H. So it needs more space. So what will happen to this geometry? You're talking about a lot of geometry here. So basically, this will try to go like this. It will become a helix. So that is what happening in our DNA also. Because of all those side things, it has to keep on twisting to make it a twisted helical structure. So along with these proteins, lipids, these are all you heard. So these are the 4 major types of macromolecules. I didn't use that word macromolecule. The other term for polymer is macromolecule because it's a huge molecule. That's the meaning of it. So in plants, polysaccharides is the most important class of all your cellulose and the various things that you meant. They all come under this class of polysaccharides. But in our body, for example, proteins, lipids, and nucleic acids. These are the most important things. In addition, if you look at muscles and other things, except our bonds, which is made up of calcium and other minerals, and tooth and other bonds, that is also a composite of polymer and inorganic materials. It's not also pure inorganic material. So you have all of our body is made up of polymers, whether it is proteins, whether you're talking about cells, other things. So it's a very important class of material. So this is a formation of protein, how complex it is. So this, we were talking about very simple molecules and all. Now, if you want to understand these molecules, they are much more complex. For example, a protein is something, these are natural molecules formed from 20 amino acids, we all know that. But the problem is that it starts like this, then it forms what are known as secondary structures, and then what are known as tertiary structures. So those tertiary structures is what we were seeing here as, those ribbon-like structures and things like that. So they become much more complex. So when you apply force, etc., is the force going to this tertiary structure, or is it getting transferred to secondary structure, or is it going to primary structure? We don't know, right? So, and in the presence of various other, for example, in biological systems, they are also sitting in the presence of water, right? Our cells are full of water. Bodies, how much percentage is water? 70% is water, right? Or maybe more than that. So which means all these molecules are also interacting with water all the time. So interesting things happen there. A lot of exchange with water happens with various atoms like minerals, and all those things are also transported back and forth in the presence of these tertiary structures. Okay, so this is another polymer which is present in plants. Okay, so have you heard of pectin? Have you all eaten jam? Yes. So have you all eaten jelly? Also, yeah. So now let me ask a question. Is jelly solid or a fluid? Semi. What is meant by that? Neither here nor there, right? So as I said, you can have this you call as solid at the moment. Okay. And what is the fluid polymer? Blood, for example, when you see it, you will call it as a fluid, but it's also not fluid, which it's particles in water. Let me say, yeah, jelly is something which I wanted to tell you. So jelly, when you take it, why do you say it is a solid? No, you didn't say it's a solid. You said it is neither here nor there. But how do we know it's something is solid? Not rigid. Shape is important, right? So the solids have shape. And then what happens if I apply a force to solid?
Doesn't change its shape.
No, it changes its shape. See, it's changing its shape and it goes back. So you have all done something called Hooke's law.
Yeah.
Right? Hooke's law is stress is proportional to strain. All solids, if elastic solids, what we call, they obey Hooke's law. So then you stretch them and release, they'll go back. and without losing anything. So that's what we call as solids. Then there is another class called fluids. Like if I take oil and I smear it in my hand, let's say I have a drop of water or oil. So I'm applying force, or your shampoo, something like that, okay? And I'm applying force. What happens? So from that, it changes shape. Will it go back when I remove hand? What happens to it? It continues to flow if I go on applying force. But if I stop applying force, it doesn't go back to its shape. So by shape also again we can define something. Now when it comes to this jelly, what happens? Does it have a shape? It has a shape. When I shape it in something and then give it to you, it has a shape, right? So isn't it solid? Apply force, it doesn't go back. So that if I apply force to a glass also, it doesn't go back. It will crack. So is it like that? No, but here you can also see some fluid coming out. So where is that fluid sitting? So this is a very interesting question about polymers. So they actually, so some of the applications of this pectin is, you can see your jam there, okay? And jam and jelly and things like that, okay? And also some patches and things like that, which, so this particular polymer, pectin, which you can extract from lemon peel and things like that. It is used in various applications like thickening of jams and jellies, and also some other applications like when you, for example, when you go to hospital, they apply some kind of a gel on your, even your hand sanitizer. It is also in what is known as a gel. Okay, what is that material? Any idea? So these are also polymers. Only thing is that, you have this polymer chains lying here like this, okay? And they're connected, interconnected, and with some water in between, lot of water. So if I take out the water, it will be solid polymer. If I put that, but the water is held inside that network of things. So when you apply force, etc., they behave like both solid and fluid, both combined, because both are there embedded. Okay, so those gels are some cross-link systems like that. So I work actually, pardon? They are actually, I'm coming to that. So as I said, the classical materials which obey Hooke's law are called elastic solid. The materials which obey what is known as Newton's law of fluids. You have heard of it? So in the case of, I don't know that you guys have done it, but I'll just say, Hooke's law is stress is proportional to strain, or maybe you are using epsilon, I don't know, whatever. Okay, so you can write stress is equal to some constant into this. This is your modulus, Young's modulus. You heard of it. So this is Hooke's law for elastic solids. Okay. So similarly for fluids which are ideal, this is again ideal type. This sigma stress applied is proportional to strain rate. Okay. Strain rate. Right. So there, proportional to. So there is a constant again here, that is mu or eta, that is a viscosity, and you write like this. So these are Newton's law for fluids, and they obey Newton's law, or these are also Newtonian fluids in some sense. Now my question is, if there are things which are in between, okay, is it possible to have a combination of these two? Okay, materials which are neither elastic solids. I'll tell you why it is. See, this elastic solid, if I plot, okay, stress and strain, it is a straight line, and the slope is what your modulus, right? Now, when this test is known as I told you, I take the rubber band, I stretch it. Okay, so if I hang 1 kilogram of force, I know it's 1 kilogram. If I know the area of cross section on which it is acting, I can calculate stress. And I know how much it is. If I mark 2 points on that rubber band, you can go and do this experiment if you want. I can calculate what is the deformation, epsilon. Is it clear? So, right, so this, if I know the stress is force by area, and this is some delta, let's say you have taken this was L. So when you apply the force, it gets deformed to L plus delta L. So that delta L by L is your epsilon. So you can do that simply. That so when I do it with the metal, some metal wire, if I take and do that, it will look like this, some perfect graph I get. But if I take a rubber band and do it, you have any idea how it looks like? This graph? This graph doesn't look like this. For the rubber band, the graph will look like this. Now, how do you put that equation? Can I put that stress is proportional to strain? No, right? I can do some piecewise fitting or something like that, right? So it's not. So basically, we find that they are actually not obeying the Hooke's law. And also we find that there also this rate dependency. Okay, this strain is stress is also proportional to strain rates many times. Okay, so which means polymers are not purely elastic solids, neither pure fluids. They are viscoelastic. Okay, that's the term. Okay, so this viscoelasticity is obvious in many behavior. That rubber band or the balloon that you have, first time when you blow it, it takes one shape. Okay, now let's say I put it around some few books, that rubber band, and after 1 week, if you go and check it, what will be the shape of that rubber band? If I did only once and put it out, it will go back to its original shape. Now 1 week later, if I go and check that rubber band, what is the status? Much more elongated, right? It doesn't have the original shape. So what happened is that delta L that we saw here, if I hang the weight here permanently, it will go on deforming. What goes on deforming? No, glass also is there. Glass is something very funny material again. Fluids, right? If I apply force, fluids will continuously deform. So now your rubber band is also deforming like fluid. So you can't see it, that's all. So these are very interesting materials. There is some time scale associated with it. They're all deforming. In fact, all real materials are viscoelastic. So we call that property creep. The material is creeping. Okay. So for example, if you sit here, okay, for real long time, there will be a dent because you're applying that force. So you would have seen that, if you put a refrigerator in one place in a old, if you have old floor, you'll see there is a small dent formed there because that force is being applied for a long time, and that hidden fluid behavior of the material is allowing it to deform. So there is what do you call Deborah number. Okay, that's a very famous number that you may come across some point of time. So Deborah is a old-time prophetess. In Bible, I think her name is Deborah. You can check. D-E-B-O-R-A-H. Deborah. Deborah number. So she said mountains flowed in front of the Lord. Mountains flowed in front of the Lord. That's why Deborah's name is given to that particular number. So it means the mountain looks like a solid thing to us, but for the time scale of the Lord, I mean God or whatever. So basically things are actually flowing. What we visualize is a time scale, need not be the time scale at which materials may be deforming. So they are flowing, but we can't see it. So there is a time scale at which we measure certain things, then certain time scale at which these materials are flowing also or changing with respect. So it's a very interesting material. Okay. So I work with this pectin currently. So our research is related to pectin, but you don't have to worry. So we actually take this pectin and do this deformation. Okay, and find out what all things can happen with respect to the structure, etc. Similarly, another material that I work with is a protein called casein, which is present in milk, which you said, it's very complicated one. You found? Yes, I have here mentioned something very interesting property here. This plant cell wall, there is something called stomata. So this is not yet completely unraveled. So there are so many interesting physics problems involved in, related to biology, which are not understood. For example, this simple stomatal opening is still not understood. You all study in school that, stomata closes when there is, when it is very hot and things like that. What is the actual mechanism involved? Okay, what material is actually closing and opening it, sensing the humidity in the air? Okay, so there has to be a material which is sensitive to the humidity. So what property of that material is changing? So our assumption is that this pectin is involved. So pectin is a water-loving polymer in that particular part. So it can sense the humidity in the atmosphere, but why does it change the shape? So this here, the curvature, when it is, I don't think you can see it. For example, when the stomata is opening, it's like this. And when it is closed, it becomes a line. So the cell is basically like this. So this is the opening. Okay. So what gives that curvature in the presence of, certain humidity, and what dictates it to close when there is, what? So that's a little complex for you to understand at the moment, but there's so much interesting mechanics involved with the material. Okay, maybe I'll stop here. There's a lot of things that you can go on talking about polymers. Okay. One more interesting thing I'll tell you, and then because somebody said about glass. Do I have time? 5 more minutes. Okay. So somebody said about glass, right? So this polymer now, because it's very big molecular weight and all, so it doesn't exist like your gas, solid, liquid, physical states. What physical states are possible? So I have put there already on the slide. So it is only, what we can see is solid state. Okay, but actually it is not only solid. That solid state itself, there is an interesting thing. I don't know anybody has seen this movie called Terminator 2. Maybe it's an old movie. Maybe go and check it. In that, apparently, I have also not seen it, but I have heard the story because it's of interest to me. I caught this. There is somebody being put into liquid nitrogen tank, a human being. What will happen? You'll freeze and die is what you will think. But if you take out the person, No, it's not under high pressure. Have you seen liquid nitrogen? If you put liquid nitrogen, have you heard of?
Yeah.
What is its boiling point? Minus 180. Okay, it's very, very cold. So if you put a leaf, for example, okay, in that and take it out and drop it. Leaf is under normal temperature, very flexible. Nothing will happen. But if you put it in that liquid nitrogen and put it on the ground, it will shatter like glass. So it's a very interesting property. So because again, polymers are involved there. There is something called glass transition. Because somebody said glass, right? All polymers, including us, okay, because we have made, that's an example also. If we jump into a liquid nitrogen tank and put yourself out there, you will shatter like glass. Don't go and try your hand or anything in liquid nitrogen, okay? It will not come back. Though ideally, all these dead polymers, actually I can bring it back to normal temperature if I just allow it to come back. It's a back and forth process, reversible process. But for living systems, if you do that, it may become an irreversible process. So it undergoes what is known as a glass to rubber transition. Okay, so when most of our body is in what is known as a rubbery state. Okay, so so each polymer has a characteristic glass transition temperature below which it is glass. all polymers, including biological, synthetic, everything. That polythene bag also, if I take it below its glass transition, it will be glass. It will shatter like glass. So again, a lot of interesting things about this, whether it is solid, liquid, all coming in. And you all know that, you can heat it and what will happen? It will melt and flow, right? So that is how these are all processed. So in solid state, I can process it. To get this shape, I have to apply pressure and temperature. So then they'll start flowing really like a Newtonian fluid, like water. Okay. And then I cool it, suddenly, then it will get into this shape. Okay. So that's how they are all made. So this is about polymers. If you have some questions, you can ask me. Because he was talking to you about some geometry and shape, I'll throw in problem for you, which I am interested. If you find solution, you can let me know. I'm trying to design something using polymer, of course. But I want an architecture or a geometry in which I want to have maximum volume being stored in minimum surface area. Maximum volume of material, some fluid I want to store, okay, in minimum surface area. What would be a geometry? For example, you would have seen plant, leaf, for example, if you see the veins, right? What we call as veins, right? So they have a special way of arrangement. Huh? Pardon? Not xylem phloem. If you take any plant leaf, how the fluid is going through that, it's a two-dimensional object. If you look at the leaf, most of the leaves, but they're able to reach all the periphery of the leaf using that particular architecture. I want to design something like that. What would be your suggestion? It can be any shape. I don't mind what is a physical shape. It should be 2D object, okay, and with maximum volume storage. Yeah, I mean, in the sense, I want some volume, some fluid. I want to put some water. Let's say I want to put 30 ml of water, but I don't want to take too much surface, large area. The object should be very compact in terms of 2D organization. Now, you are all very young. I'm sure this is the right crowd which should get me the answer. This has to also do with, if any of you are interested in, doing some design, you can also probably associate with me. I have been looking for some, really motivated girls or women who can help me with this. I'll explain to you the problem. I don't know, are there engineers here? Engineering students? Raise hands, okay. Which branch? Electronics. And you? Civil. Okay. Yeah, it doesn't matter. Now you're all in first year. It doesn't matter, I think, which area, branch, etc. So what I'm trying to design is something to do with women. Okay. So it's basically something to do with menstrual fluid collection. Okay. So come up with an outlandish design to do this. Yes, you are in the right path. That's the kind of question I'm trying to address. But the problem is, physically, when we want to design, there are constraints. Okay, what is the volume through which these fluids, for example, are non-Newtonian fluids. So they are not Newtonian fluids like water, maybe it's easy. And also the problem with it's complicated. For example, I also want to repeatedly use it. In the sense I want to empty it. Okay, and wash it and reuse, for example. So I not only want to collect the fluid, I also want to empty it. So, so what is the minimum dimensions that you can go for? Because when the dimensions become smaller and smaller, it's like our blood flowing through our veins also. They reach through to very small micro capillaries, right? So, so there is a pressure loss and things like that associated with it. But if you want to reverse flow it, what is the situation? I can store it once, but can I take it out? So that's the question. There's no solution existing. So these are the kind of problems we want to solve, where maybe there is interface between mathematics, maybe people who think in terms of materials, some people who work with engineering solutions, fluids, all combined together. Okay. Any questions? Yes. See, it's menstrual cup is very difficult to use. That's why I want to, it should be an outside phenomena, right? If because whatever is what we are currently using are non-environment friendly materials, which when we throw it, all those pads and things like that. So if you want to use menstrual cup again, it's insertable, and many people are not very happy to use it. So there should be something that is interfacing so that it comes out, but at the same time reusable. So there is a that menstrual cup or moon cup is a polymer which is again silicone rubber based. Okay, it's very flexible, biomedically non-interacting with the human body, so it's insertable inside the body. But it is very uncomfortable and inconvenient to use. So you have to come up with something which is between your sanitary napkin and at the same time a moon cup. Yeah. Interesting? Yeah. Yes. Okay. I hope you learned something about polymers. Okay.